In 3.4, our objective is to use derivatives to determine the concavity of a function, points of inflection, and relative extrema. First, let's talk about what is the difference between concave upward and concave downward. Your first picture is a snippet of a graph where this part of the graph is concave upward. Concave upward specifically means that the curve lies above its tangent lines. The curve lies above its tangents. Notice when I draw a tangent line anywhere, the curve is bending upward above the tangent lines. The curve lies above the tangent lines. Concave downward is the curve lying below its tangent lines. So if I draw the tangent lines anywhere I pick, the curve is bending below those tangent lines. And it's sometimes easier to see if you draw the tangent line longer. If you draw it longer, you can see the curve bending downward below versus concave upward. If I draw the tangent line longer, you can see the curve bending upward above the tangent lines. So the curve lies above its tangents or below its tangents. Let's explore more of what this can tell us about a function. If I look at each of these tangents, the slope of the first one is a negative slope. Then it's a positive slope. As I move to the right, it becomes steeper, more positive, and then more positive. So what's happening to the slopes of these tangent lines? They are increasing. The slopes of the tangents are increasing. We'll think about what that means in terms of when we talked about increasing and decreasing functions. If something, a function, is increasing, well, first let's say this. Let's translate slope into our synonym for slope. Slope is derivative. So let's call that f prime if we're looking at a function of f. So let's say this curve that we're looking at is f of x. Similarly over here, we'll say this is another portion of f of x. So f of x is our blue curve. The derivative, the slope of f, can be called f prime. So instead of saying the slopes of the tangents are increasing, f prime is increasing because f prime means the slopes of the tangents. So now let's think back to when we say something is increasing, what that means about that something. Well, if something is increasing, in this case f prime is increasing, the derivative of that something is greater than 0. So if f prime is increasing, its derivative is positive. Well, what does that simplify into? Therefore, that's two derivatives. So the second derivative is positive. When a function is concave upward, the second derivative is positive. Now, even though that's the bottom line that we want to use today, we cannot leave out all these other steps. F prime is increasing. Also a very important part of a function being concave up. Let's look at that similarly for concave downward. The curve is lying below the tangents, and if I look at the tangents, this is a positive slope. This is still positive, but it's a little bit less positive. This is still positive, but it's getting less steep, so less positive. Now this one has a negative slope. So what's happening to the slopes? They are decreasing. Really positive, less positive, less positive, and now negative. So in this one, the slopes of the tangent lines are decreasing. And let's translate that into what we know about derivatives. So therefore, f prime, slopes of the tangents, derivative, is decreasing. Remember, slope means derivative. So we're just taking out the word slopes of the tangents and putting derivative in its spot. Well, what does that mean? Its derivative, f prime, is decreasing, so the derivative of f prime is negative. Well, what does that lead us to? That's right, the second derivative, prime prime, second derivative, is negative. So here's what we want to take out from this exercise. Concave downward, the second derivative will be negative. F prime, the first derivative, will be decreasing. Let's take a look at a graph that has a bunch of concave up and concave down pieces all put together. And let's identify where we see concave up, where we see concave down. So concave upward, on what intervals do we see that? So it looks like, and we're going to estimate from about 6 to about 8. It looks like concave upward, so 6 to 8. Union, so I find another interval, looks like here, from about 10 to about 13, 10 to 13. Can you find any other intervals that are concave up? Let's list them all. 13 to 14. I can't say all the way from 10 to 14 because here there's a cusp, it's pointy, there is no derivative there, there is no tangent line. And if I can't draw a tangent, I can't say if the curve lies above or below it. So we stop at 13. Let's identify where the function that I'm looking at is concave downward. So concave downward from this point from 1 to about 6. Can we find all the other ones? 8 until 10, and 14 until 16. So 8 to 10 and 14 to 16. Now where the concavity changes, those things are called points of inflection. Points of inflection. Those are where the concavity changes. Points of inflection or inflection points. I like to abbreviate POI for short. Points of inflection or POI for short. Those are points. Those are X, Y coordinates where concavity changes. Here is a POI because I see concave down changes to concave up. So that is a point of inflection. The ordered pair is 6, 3. So the point of inflection, 6, 3. That's one point of inflection. Let's list the points. This is different from intervals. These are points. Points are ordered pairs. Here's another point of inflection at 8, 3. Concavity also changes at 10, and it looks like it's at about 5.5. So 10, 5.5. And one more point of inflection at 14, 4, it looks like. 14, 4. Those are our points of inflection.